Hey folks, welcome to the Internet Congestion Control Research Group. This is Reese Enghart. I'm acting as a delegate for ICCRG today because the chairs unfortunately couldn't make it to the meeting. Please, for those in the room, please join our Meet-Echo session by scanning the QR code up front or by using the link from the agenda. And also please remember to wear your mask unless you're speaking at the microphone or briefly for drinking. So here's a reminder of our Note 12 specifically for IETF sessions. So this is not an IETF session, but we are following the IETF's IPR disclosure rules. If you're not familiar with those, please read up on them. Also, quick reminder that we are recording the presentations and anything people might be saying at the mic. So if you participate online, turn on your camera and your microphone, then you will appear in such recordings. And if you participate in person and speak at the microphone, you may also appear in our recordings. And then finally, our usual privacy notice and code of conduct also applies. And if you're not familiar with those, I invite you to familiarize yourself. Quick reminder also that the IETF, the Internet Research Task Force, conducts research. We're not a standards development organization, and we can publish documents, but our primary goal is to promote research collaborations in exploring research issues. And so our main goal is to generate insight, and we will have two hopefully insightful talks today. But first, I just wanted to ask if we can please get another note taker. Would anybody be willing to take notes for our discussions that we are having? Okay, I see Anna. Anybody else volunteering as backup or? All right, thank you, Anna. We have two talks on our agenda. Oh, and we also have somebody in the chat volunteering as backup. Thank you, Benson. So we have two talks today, and without further ado, I am going to share those slides and then pass it to Ayush. Okay, hang on. Sorry, Ayush, can you request slide sharing yourself, please? Because for some reason, I cannot share your slides right now.
Oh, okay, sure. I can't see my slide deck.
Yeah, it is still being loaded, I suppose. Oh, okay, let's try that again.
Nope, they're still not there.
Okay, I think I got it now.
Okay, great. So do I have control of the slide deck or?
And now you should have control of the slide deck.
Okay. Yeah, that works. Thank you. Okay. Hello, everyone. I'm Ayush. I'm uh, finally a PhD student at NUS. And today I'll be sharing one of our papers called Are We Heading Towards a BBR Dominant Internet, which was presented in IMC last year. So this entire work was actually motivated by the fact that BBR was quickly gaining traction once it was first introduced in 2016, and early adopters were reporting higher throughputs and lower delay jitter after switching to BBR from traditional congestion control algorithms like Cubic. And according to a measurement study that we did in 2019, it was clear to us that these performance gains were not going unnoticed by the rest of the internet as well. So in late 2019, when we did a measurement study of the top 20,000 Alexa websites, we found that BBR actually accounted for 18% of the websites that we classified. And in terms of traffic share, because most of these websites actually streamed video, BBR was controlling close to 40% of the downstream traffic on the internet. So clearly, the trend that we were seeing was that BBR is becoming a dominant force in the internet's congestion control landscape, and a lot of it seemed to be motivated by BBR's performance gains over Cubic, more particularly BBR's throughput gains over Cubic. So given this trend, the research question really that me and my research team wanted to answer was that given that BBR is performing really well on the internet today, are we heading towards an all BBR internet in the near future? Or can we expect BBR to completely replace Cubic on account of its performance benefits over traditional congestion control algorithms? So to answer this question, we actually had to answer two sub-questions. The first thing we wanted to understand was how will BBR's current throughput gains evolve as more flows on the internet start running BBR? So as people start realizing that BBR actually performs better and they start switching from Cubic to BBR, how's that actually going to impact the performance gains that current BBR flows are seeing? So for this, I'll be briefly going over a mathematical model that we built to model the steady state behavior of competing cubic and BBR flows. And the second question that we want to answer is that given whatever trend in throughput gains we can expect to see in the future, how will this actually impact the future congestion control landscape? And for this, we actually extend our mathematical model to help us perform a game theoretical analysis that sort of treats Cubic and BBR as two separate strategies to optimize a certain utility on a network. And then we sort of try to predict how this game will play out and in turn dictate the future of the internet's congestion control landscape. So as we all know, and I'm sure I don't need to present this primer to the ICCRG, but just as a reminder, Cubic is currently the most dominant congestion control algorithm on the internet, and this is what BBR is poised to replace today. So Cubic is, as we all know, is congestion based. It uses packet loss as a congestion signal, and when it sees a packet loss, it backs off. And because it only backs off when it sees a packet loss, it's often referred to as a buffer filler because no matter how deep your buffer is, Cubic is going to fill the entire buffer till it sees a packet loss, and only then it's going to back off. BBR, in contrast, does not elect to use packet loss as a congestion signal. Instead of that, it elects to build a model of the network, which is based on the minimum RTT and bandwidth estimates. And based on this model, it sort of figures out what the correct number of packets should be and then sets its sending rate accordingly. So what's crucial to BBR is that because it's model based, the measurement of this bandwidth and minimum RTT is very crucial to BBR operating correctly. So what BBR does to measure the minimum RTT, for example, is that all BBR flows collaboratively back off every 10 seconds to empty the bottleneck buffer in order to measure the minimum RTT. And actually, it's this mechanic which introduces the problem when Cubic and BBR interact. So we know that BBR wants to empty the bottleneck buffer every 10 seconds, and the measurement that it makes when the bottleneck buffer is empty is super crucial to BBR working correctly. But on the internet today, BBR is actually competing with Cubic, which is a buffer filler, and it will not collaboratively empty the bottleneck buffer when BBR wants to. And this introduces something called RTT overestimation in BBR, which often tends to make it more aggressive when it's competing with loss-based congestion control algorithms. And this RTT overestimation actually comes because when BBR flows back off, they actually don't see a completely empty buffer. They still see some residual packets that are left behind by a competing loss-based, or in this case, cubic flow. And then these residual packets contribute to a bloated RTT man estimation, and in turn, BBR becomes even more aggressive. So in this paper, when we were modeling the interactions between cubic and BBR, I think this is the key mechanic that we wanted to explore and see how it impacts fairness and competition between cubic and BBR flows. So before I go into the details of the model itself, I think it's valuable to go over the assumptions that we make so that we can put the results that I'm going to present later in context. And then we can also discuss what happens to our results when we start suspending each of these assumptions. So starting for the simplicity of the model, we assume that all the competing flows have the same RTT. So this is one of the stronger assumptions that our model makes, because even though most of your traffic on the internet today is delivered by CDNs, which sort of reduce the window of RTTs that you can see, that doesn't mean that there's no RTT diversity on the internet today. You'll still see flows with different RTTs. But for the simplicity of the model, we assume that we have similar RTTs between flows. And then later on, I'll present results and show what happens to the predictions of our model once we suspend this assumption. The other four assumptions we make are somewhat more reasonable than the similar RTT assumption. We assume that the buffer is at least 1 BDP and the link is always fully utilized. From previous results, we know that when BBR competes with loss-based flows, it tends to be C-wind limited. So we assume that BBR flows always have twice their BDP estimate worth of packets in flight. We also assume that the packets are uniformly distributed, the buffer is drop tail, and BBR's reduction in bandwidth while probing for RTT min is negligible. So once we have these assumptions in place, really what you need to model the interaction between cubic and BBR are three key quantities, and you need to model them only in the steady state because we are interested in the steady state. So the first quantity we model is, of course, the throughput of the competing cubic and BBR flows, which we simply set as the C-wind a flow might have divided by the total end-to-end delay that they see. So over here in equation 1, we can calculate BBR's throughput as twice its BDP estimate. And notice over here, to calculate the BDP, I'm not using the RTT, but RTT plus, which denotes BBR's overestimated RTT. And this is divided by the end-to-end delay that all the flows see, which is the base RTT plus the queuing delay inflicted by the packets that are queuing at the bottleneck buffer. The second quantity we need to calculate is the RTT overestimate itself. So since, as I just discussed, BBR's RTT overestimate is actually created by the residual packets that cubic leaves in the buffer when BBR tries to probe for the minimum RTT. So in this case, we calculate RTT plus as the base RTT plus the amount of residual packets in the buffer divided by the amount of time it'll take to drain them, which is simply your link capacity. And the last piece of the puzzle is figuring out how many residual packets a competing cubic flow is going to leave when it's competing with the BBR flow. And this is fairly straightforward to calculate because we know that a cubic, given a maximum window for a cubic flow, we know it's going to back off to 70% of its window size when it sees a packet loss, and then we can simply subtract the BDP and figure out how much is left over in the buffer. So for our two-flow model, actually, we can just take these three equations with a couple of more general equations and just solve them as a set of linear equations and derive the bandwidths that the competing cubic and BBR flows are going to receive. So I won't go into the details here, but basically when you solve the math, this is the equation that you get for cubic's throughput. And because we assume that the link is fully utilized, you can just subtract this value from the link capacity to calculate what BBR's throughput is going to be. So to validate our two-flow model, we actually ran a competing cubic and BBR flow over a variety of network conditions with variety of buffer sizes, and we pumped these numbers through a model as well as calculated the throughput empirically over a real test bed. And as you can see, our simple model, which is based on only the steady state behavior, actually predicts the throughput of the competing BBR flow with reasonable accuracy. And this is actually true in um, network conditions other than the one presented on this slide. You can check out these network conditions in the paper for more details. So we know that our simple two-flow model works really well, but as we all know, the internet has more than two flows. So we need to augment our model from two flows and make it work for multiple flows where you have multiple cubic and multiple BBR flows competing. So what changes when you have multiple cubic and multiple BBR flows compete? Well, it turns out there's only one key thing that changes when you're trying to model how BBR flows and cubic flows interact. And that's actually the number of residual packets that the cubic flows are going to collaboratively leave in the bottleneck buffer during BBR's probe RTT phase. So if you think about it, for a single cubic flow, we know that it's going to back off by 70% whenever it sees a packet loss. So it's very straightforward to calculate. But when you have multiple cubic flows, depending on whether their back off behavior is synchronized or not synchronized, you can actually leave different amount of packets in the bottleneck buffer, and this can introduce variability in BBR's RTT min overestimate. So to solve this problem, we actually do away with a single equation and we move to predicting bounds, which are based on two scenarios. The first scenario is when all your competing cubic flows are perfectly synchronized. So in this scenario, we're assuming that all the cubic flows back off together. And then the other bound that we calculate is the scenario where all your cubic flows are perfectly desynchronized. So this would mean that only one cubic flow backs off at any given time. And we assume that in any given network, the actual behavior is going to lie somewhere between these two bounds. So now what we can do for the multiple flow model is that we can simply replace our single equation, which was for a single cubic flow, by these two bounds. And now we can calculate two bounds instead of a single solid line. So that's exactly what we did, and we validated its predictions for multiple flows. So in this experiment, we have launched 5 cubic and 5 BBR flows, and we varied the bottleneck buffer size in multiples of the BDP. And then we show how our predicted region, which is highlighted in light blue, compares with the empirically observed values, which are the black squares on this graph. And again, we see that the actual throughput is within the predicted bounds of a reasonably simple model. So we know that our model works reasonably well for two flows as well as for multiple flows. But let's take a step back and ask ourselves why we actually set out to do all this modeling. So the reason we wanted to do this modeling was we wanted to understand how BBR's throughput gains are going to evolve as more flows at the bottleneck start switching from cubic to BBR. So what happens to BBR's throughput when more flows are running BBR and less flows are running cubic? So to look at this behavior, I'm in this graph, I've plotted the empirically observed throughput as well as the throughput predicted by a model for uh, a given BBR flow. And in this experiment, we ran 20 flows. And across each iteration, we progressively switched one flow from cubic to BBR till in the end, we had all the flows running BBR. And in each of these scenarios, with each of these different distributions, we calculated BBR's average bandwidth and saw how it evolves as more flows switch to BBR. So the key trend that we actually see in this graph is that as the number of BBR flows at the bottleneck increases, their per flow average bandwidth decreases, which means that in a given network, as more flows start switching to BBR, BBR's throughput gains over cubic are going to diminish. And in fact, they seem to diminish exponentially in this graph. So we know that BBR's gains are going to go down as more people switch from cubic to BBR. But the question we want to answer now is how low is too low? Or is there a point at which that BBR starts performing so poorly that cubic starts becoming competitive again? So to answer this question, I'm going to define a new quantity called the Nash equilibrium distribution of cubic and BBR flows in a network. And for this distribution, what I mean by this is that a given distribution of cubic and BBR flows in a network is the Nash equilibrium distribution if none of the flows have the performance incentive to switch algorithms. So let's say if in a network, the Nash equilibrium distribution lies at 5 cubic flows and 5 BBR flows, that means that none of the cubic flows benefit anything from switching to BBR, and none of the BBR flows benefit anything from switching to cubic. And the reason we model this quantity this way is because if you assume that the websites on the internet are going to A/B test cubic and BBR and decide between them based purely on performance, then our calculated Nash equilibrium is most likely what the internet's congestion control landscape is going to move towards. So let's actually see what this Nash equilibrium might look like given the trend that we have already seen in BBR's diminishing returns. So over here, I've plotted a very general form of the graph that I presented earlier. So on the y-axis, I have BBR's per flow bandwidth, and on the x-axis, I have the number of BBR flows at the bottleneck at any given point. And we are already familiar with the exponentially decreasing gains of BBR. One additional thing I've done in this graph is you'll notice I've added dotted line, which I call the fair share line. So this fair share line is basically the fair share bandwidth at the bottleneck. And what this means is that if your red line dips below the fair share line, that means that your BBR flows are getting less than their fair share bandwidth. And if the red line is above the fair share line, that means your BBR flows are getting more than their fair share bandwidth. And because in this case, we assume that the bottleneck link is completely utilized, BBR getting less than the fair share bandwidth directly translates into competing cubic flows getting more than their fair share bandwidth. Or in other words, that would mean that if your distribution lies in the blue region of this graph, BBR flows generally do better in that network. Whereas if your distribution lies in the green region of this graph, that means that your cubic flows are doing better in your network. So we know this is what the graph is going to look like, but where is the Nash equilibrium going to lie on this graph? And this is important because Nash equilibrium is going to basically predict what the future of the internet is going to look like. So let's actually look at the point that I've highlighted in yellow on this graph, which lies at the intersection of the red line and the fair share line, and try to understand what happens when flows try to switch algorithms at this distribution. So at this distribution, where the BBR flows are getting the fair share of the bandwidth, if a cubic flow tries to switch to BBR, the distribution is going to move towards the right, or basically the distribution is going to enter the green zone where cubic flows are doing better, which means that at this distribution, the cubic flow does not have the incentive to switch to BBR because it's only going to do worse. Conversely, if the opposite happens, where a BBR flow tries to switch to cubic, now your distribution is going to move to the left of the graph, where you enter the blue region where the BBR flow is actually superior. So again, your BBR flow does not have the incentive to switch to cubic at this point again. And this is actually quite perfect because this is exactly what our what our definition of a Nash equilibrium distribution is. So based on the simple interaction and given how BBR's performance gains evolve, we know that the distribution at which all the flows are getting their fair share basically represents the Nash equilibrium distribution of the competing congestion control algorithms. So we can take this result, we can use it to augment the throughput model that I presented earlier, and now we can start calculating the Nash equilibrium distributions in different network conditions. So that's exactly what we did. Again, over here, the predicted Nash equilibrium exists in a region, and we don't predict a concrete point because our multi-flow throughput model predicts two bounds and not a solid line. So as we can see, in this on this slide, basically in this experiment, we ran 50 flows through a 50 Mbps 40 ms link and tested all combinations of competing cubic and BBR flows and empirically calculated um, where the Nash equilibria lie and compared this empirically calculated Nash equilibrium with the Nash equilibrium predicted by a model. So the first thing again that we notice here is that our model again does a good job of predicting the general region in which these Nash equilibrium is supposed to lie. And we also see that the majority of Nash equilibrium distributions actually have cubic flows, which means that despite BBR throughput gains over cubic when you have small number of BBR flows, in variety of buffer sizes, you're actually going to see mixed distribution, the network settle on a mixed distribution of cubic and BBR, or basically that cubic is here to stay on the internet if our model is valid. Well, all this is true unless, of course, the buffers on the internet are extremely tiny, because when your buffer size is less than 1 BDP, then BBR is the clearly dominant strategy, and then everyone should converge to using BBR. The last thing that I want to go over is actually suspending the earlier assumption that I mentioned. So early on, I mentioned that we assume that all the flows have the same RTT, but what actually happens when you remove this assumption and you start giving flows different RTTs? So in this case, I've only plotted the empirically observed Nash equilibria and not the region predicted by our model itself, because our model only predicts for flows that have the same RTT. And the first thing that we see is that, again, Nash equilibria does exist for scenarios where different flows have different RTTs. And again, these Nash equilibrium distributions are mixed distributions, which means that they have both cubic and BBR flows. Other than that, another key trend that we saw was that when you have flows with different RTTs competing, the flows with the shorter RTT tended to adopt cubic over BBR, and the flows with longer RTT tended to adopt BBR more than cubic. In the paper, we go over why we think this is because of how RTT fairness works in cubic and BBR differently. Lastly, we all know that BBR is slowly going to be phased out by BBR v2. So we were also interested in seeing how our predictions actually fare when you replace BBR flows with BBR v2. So over here, the blue region is the region predicted by a model for BBR. And the points are the empirically observed Nash equilibria in all these different network conditions. And the first thing that we see is that our model seems to overestimate the number of cubic flows at the Nash equilibria. And the reason this happens is because in general, BBR is more aggressive than BBR v2. So in summary, we present a mathematical model that predicts the throughputs for the steady state interaction between cubic and BBR. And we show that as the number of BBR flows increases at the bottleneck, the throughput advantage will reduce. And we also show a game theoretic analysis to show that in most networks, the Nash equilibrium distribution of cubic and BBR flows is going to be mixed. Before I end the presentation, I think it's important to contextualize the key results that we've got from this paper, because there was a brief discussion on the BBR Dev mailing list about this paper, and there were some interesting points brought up about how context matters when you're actually trying to figure out how different flows are competing. So I think it's worth noting that this paper only explores the steady state behavior of bulk cubic and BBR flows. And for more complex workloads with different flow sizes, we'll probably have to utilize more accurate fluid models that also model the transient states for cubic and BBR. And the exact Nash equilibrium, so we predict some Nash equilibrium distribution in the paper, but of course the exact Nash equilibrium distribution is going to depend on a variety of factors, which is going to include network characteristics, the flow sizes, as well as the choice of your network utility. Because over here, we only assume that people care about throughput, but in the real world, different flows optimize for different things, ranging from QoE, delay, or any combination of each of these factors. So how do you actually, so we know it's a complicated problem. We've solved it for a very simple case, but how can you actually figure out if there is going to be a mixed Nash equilibrium in your network? So I think if we abstract ourselves out from all the details of the model and the actual distribution of the predicted Nash equilibria, we can still have some intuition as to whether we can expect a mixed distribution of BBR or cubic flows in a given network or not. And for this, again, I think we need to think of the graph that I presented earlier, where we plot the network utility for the competing BBR flows and try to figure out how they evolve as more flows in the network start running BBR. And the key question here to answer is, does the per flow utility for the BBR flows go down as the share of BBR flows increases? We have found this is true for throughput, but this might not be the case depending on what network utility you care about. Especially because throughput is a unique network utility that is a zero-sum game. If you're trying to optimize for, let's say, delay or some other parameter that's not strictly a zero-sum game, you might get varying results. So yeah, really what you need to care about is whether BBR's network utility is going to diminish as more flows start running BBR or not, or basically that given a network utility that you care about, do the BBR flows hurt themselves more than the cubic flows hurt BBR flows? Stemming from the, the results that we've seen in this paper, we also want to answer a lot of other future questions, one of which is whether a purely performance-driven switch to a new congestion control algorithm on the internet is even possible. So in this paper, we have discussed the interactions between cubic and BBR. Someone might come up with a new algorithm, but there might be a general solution that says that a performance-driven switch to a new congestion control algorithm is never possible unless your new algorithm is horrendously unfair to the competing congestion control algorithms. The other engineering question I think that we need to answer, and I think this question is a little more urgent, is how do we actually tame the zoo that that today's internet congestion control landscape has become? So we have all these different congestion control algorithms running on the internet. How do we design in-network solutions that don't just work for AIMD algorithms, don't just work for BBR, but actually work for both these classes of algorithms? And the last question that we have sort of explored, and this was also presented in IMC last year, is how much worse this heterogeneity is going to get with quick congestion control. So as we know, most of these standard algorithms are going to be re-implemented in all the numerous quick stacks. And what we found out is that not all these implementations are exactly the same. So you have the sort of speciation going on where different implementations of BBR actually perform differently, and that's increasing the heterogeneity on the internet even more. So yeah, that's all I have for all of you today. Thank you for your time, and I'll be happy to take any questions you might have.
Thank you, Ayush. Does anybody have questions? I already see Yoshifumi in the queue, please.
Hello, my name is Yoshi from AWS. This is very interesting presentation. Thank you so much. I have actually two questions. The first question is, have you ever compared the mathematical model and actual implementation? There might be a gap between mathematical model and actual implementation because cubic behave a little complex because it has a TCP-friendly model inside. And PBR has several phases. And the second question is I might be wrong, but it seems to be you presume drop del Q in the middle box. But let's say if we use ECN or Pi or Codel for AQM, does it affect your result? That's my second question.
Okay, so I think both of your questions are very valid, and they actually question the key assumptions that we make in our model. So the first question I think was regarding how well our model can predict the actual implementations of complex algorithms like cubic. So in our model, we are not interested in exactly modeling, let's say the C-wind evolution graph of cubic, or exactly modeling all of the transient states of cubic. We are more interested in what the steady state bandwidth shares between competing cubic and BBR flows are going to look like, which is why we use sort of estimates to predict what the throughput shares are going to look like. And under our assumptions, it seems to work reasonably well. But of course, it's only a model for the steady state. It's by no means a replacement for a more accurate fluid model or a simulation. So of course, our model has gaps there. With regards to your second question, where we assume that the queue is only drop tail, yeah, I think the results are going to completely change depending on what AQM you're running. Right now, we are only evaluating drop tail with different buffer sizes, but with ECN, with Pi, with Codel, things are going to drastically change. On our end, we have empirically run experiments over Codel, and we have seen that even though we don't have a model, we have seen that a Nash equilibrium runs when exists when you run Codel at the bottleneck as well. But yeah, we haven't checked ECN or Pi yet.
Thanks so much.
Okay, Andrew.
Andrew McGregor, Fastly. I think I can comment a little on the RTT distribution as seen by a CDN. The RTTs vary by a factor of about 200, from well under a millisecond to about 125-ish. Depends on where you look. The other thing is we ran a query over our sampled at the end of many connections, we sample the congestion control state and record a bunch of information about what happened to that connection at some low fraction of connections. We ran some queries over that looking for a sensible default congestion control.
Mm-hmm.
And the conclusion was there isn't one.
Yeah.
It depends. It depends on. There is usually a sensible default from any one of our pops to any particular AS, but on any larger scale than that, there just isn't really a reasonable default. Yeah. If you had to choose, you'd lean on the side of BBR because there are fewer really awful ASs for BBR, but really you want to be working per AS.
Yeah, I mean, I completely agree with you, and I think that's why we're still working on congestion control 30 years later, because we still haven't found a silver bullet solution. But yeah, maybe we can catch up later. I would be interested to discuss, what your metric was to decide whether a congestion control algorithm is good enough or not, and whether you explore things other than throughput.
I tried several, but it was usually time to last byte delivered.
Okay.
Thanks, Andrew. We had a question in the chat from VD asking if there's any results for a mix of short and long flows.
Yeah, so we haven't conducted experiments for short and long flows yet. And I mean, we did some experiments for very small number of flows, but because when you start introducing variability in flow sizes, RTTs, etc., then the state space that you need to explore increases exponentially. So we have only been able to do this for a very small number of flows, and we haven't really seen a trend that I felt was worth sharing today. But yeah, this is definitely a space that we are exploring, because there might be cases where, like how we saw for the RTT distribution, we already saw that the short RTT flows tend to prefer cubic. The same thing might be true for different flow sizes as well, where your short flows prefer one algorithm compared to the another. Yeah. So yeah, all these things are definitely things that we want to explore. Another interesting feedback that I got from a different talk was, right now I'm assuming only one bottleneck, but as your distribution of flows changes, there's also a possibility of your bottleneck moving in the network, which even further complicates the problem. So yeah, I think there are a lot of interesting details to this problem that are going to impact your exact Nash equilibrium prediction. But I think the key takeaway from our result is that such a distribution can exist, and we need to be cognizant about such a phenomenon happening on the internet, and we need to design for a heterogeneous network.
Understood. Thank you, Ayush. And then we have Jordi in the queue.
Hi. Yeah. So it looks like the situation here is like the prisoner's dilemma, where you basically you try to do bet on your own. You're going to be hurting everyone else, and so the system will operate suboptimally. Yeah. And so the solution is basically to try to coordinate rather than try to act individually. So that might shed some light on the last question, whether we can transition to whether there could be a protocol actually that we could deploy and do better off. So it would require cooperation, right?
Yeah.
And so connected to this, so with very nice you talk about the fair share, and on a single link case. The generalization of that on a multi bottleneck link case would be effectively maximum fairness, right? So
Yeah.
So and then maximum is a nice equilibrium. So we could generalize this to multi bottlenecks, I guess, and sort of and then the solution would be maximum fairness. And so then that could also shed some light, going back to 20 years ago when all the maximum algorithms, explicit rate congestion control using maximum. And if you do that, then the definition of maximum fairness is that you cannot increase the rate of a flow without hurting another flow that's equally or worse than you, right? So that's exactly the incentive that you want to create. So yeah, that might shed some light, I guess, if you wanted to transition to an algorithm that we would do all better off. Maybe revisiting some of that literature. So I don't know if you have any thoughts on that or.
Yeah, I think the hardest question to answer here is actually defining what is better off, because for everyone, better off means a different thing, and whether you're doing better off right now or so if you're doing better off right now might not necessarily mean that you're doing better off tomorrow, because it's a function of your congestion control algorithm distribution, your link speeds, other things that are going to evolve over time. Traffic patterns might change. There might be temporal aspects. So yeah, I think it's really hard to make a decision when it comes to deciding what's better for you or not. So over here, we try to model that in by someone constantly A/B testing Cubic and BBR and then switching whenever whichever algorithm performs better. But I think another thing I would like to shed some light on is that over here, we're assuming that Flow chooses only one algorithm. One way out of this problem is that instead of having one strategy, you actually start having mixed strategies. So you actually start sending some of your data over Cubic, some of your data over BBR, and then you load balance between them depending on which one performs better. So yeah, lots of interesting aspects to this problem. But
Okay.
thank you for your comment.
Nice work.
Thanks. Next we have Mohit.
Hey Ayush, Mohit here from NITK. Thanks for this interesting work. It's very nice to see the measurement studies. I just had one question. Have you been able to also look into your model about the fact that BBR inherently doesn't have a response to a packet loss? So we know that the BBR v1 did not have a response to packet loss, but I believe BBR v2 has a response to a packet loss. And more interestingly, when I looked at the source code of BBR v2 in the kernel provided by the team at Google, I could see that the response to a packet loss is pretty similar to what Cubic does. But then how has been your observations with respect to this part in your analysis?
So with respect to BBR v1 not looking at losses and BBR v2 looking at losses, of course, in our model, we assume, because we were working with BBR v1, we assume that the BBR flows are completely loss agnostic. But empirically, we have experimented with both BBR and BBR v2 flows. And what we see is that because BBR v2 flows respond to packet losses, they tend to be slightly less aggressive in a variety of networks compared to BBR v1. And because of this, you tend to have more cubic flows at the Nash equilibrium when you have BBR v2 running instead of BBR v1.
Got it. Thank you.
Okay, and then we have Björn.
Yeah, hello, Björn Teigen from Domus. Thanks for a very interesting talk. So my question is, I have a suspicion that the Nash equilibrium will be the point where the total sum of the flows, it's basically filling the link to more than sort of all the other points on the continuum, right? So is it correct to say that Nash equilibrium is the point at which the buffer bloat at the bottleneck link is the worst? Or as bad as it can be?
That's an interesting point. That we actually haven't seen the numbers in our experiments itself. Of course, in the model, we assume that the link is completely utilized at all times, but we haven't seen how that manifests itself in terms of the buffer occupancy. But yeah, that's something I need to look into. So I don't have an answer for you right now.
Okay, cool. Thanks.
Thank you.
Thanks everybody for the great discussion. If there's no further questions or comments, and I'm not seeing any, I'm going to share the other slide set. Thank you so much again, Ayush, for this excellent talk. And Stefan, you should have control over the slides now.
Can you hear me?
Yes, you're a little bit quiet. If you can turn it up just a tiny bit, maybe.
Okay, I try. Okay, thank you very much. My name is Stefan Lindner. I'm a PhD student at the University of Tübingen. And today I'm going to talk about our recent paper, Alternative Best Effort for Service Differentiation, Trading Loss versus Delay, which has been published in IEEE ACM Transactions on Networking. This is joint work with my colleagues Gabriel Paracik and Michael Ment. I'd like to start my talk with a short motivation. Why did we our work? Then I'm going to give a high-level overview of our mechanism. I will talk about one key point, namely the credit devaluation. We also implemented our mechanism in the Linux network stack. I will talk about that as well. And then finally, I'm going to show some results, how our mechanism behaves, and then I will conclude my talk. So as we all know, and as we just heard before, buffer bloat leads to temporarily long end-to-end delays in the internet. This is not an issue for bulk data transfer, general TCP applications, but for real-time applications, for example, voice over IP, this is not really desirable because voice over IP with long end-to-end delay just doesn't work. There are many different mechanisms to handle these problems. For example, the diffserv framework offers various per hop behaviors for service differentiation, where real-time traffic is strictly prioritized over non-real-time traffic, but all these mechanisms typically degrade the best effort service. So this means that best effort traffic receives worse service in this system than in a pure BE service. And this is rather controversial in the context of network neutrality. Therefore, we, and some people before us, had the idea to introduce a low delay forwarding service at the expense of additional packet loss, but with the key property that the best effort service is not degraded in any way. And thereby, users may choose whether they use the low delay forwarding service or the best effort service. And this may even lead to the point where an ISP leaves the choice of the PHB directly to the end user without their own policy. This table shows some example applications that could benefit from such a service. For example, online gaming systems typically have a requirement for the end-to-end delay of 20 to 80 milliseconds and have an acceptable packet loss rate of 5%. Cloud gaming like GeForce Now or Stadia have even more strict end-to-end delay requirements of around 50 milliseconds, but also packet loss acceptable of 5%. And then, of course, the well-known voice over IP with 150 milliseconds and 1 to 3% acceptable packet loss. Such mechanisms that provide low delay but higher packet loss are not new. These have already been discussed in the IETF. For example, in 2000, the original alternative best effort from Hurley et al., which is the basis of our work, but also in 2016, where there was a discussion about a general latency loss trade-off per hop behavior were present. However, there was no discussion about a specific mechanism. All existing mechanisms have one huge drawback. They are very complex, and most of them even require per flow state, so that it's not clear whether they are scalable internet, whether they are even implementable on common hardware. And all these mechanisms have only been evaluated in simulations, so it's also unclear how they behave with real network stacks and with modern TCP versions, for example, modern BBR, BBRv2, and so on. Therefore, we proposed a novel scheduler, which we call deadline, save credits, and decay for best effort, so the regular service, and the so-called alternative best effort, which is the low delay forwarding class. It runs locally at the bottleneck link or at the bottleneck node where the queuing happens, where the buffer bloat happens, and its objective is that best effort traffic is not degraded by other ABE traffic. Such an DCD node consists of several components. It has two FIFO queues, one for the BE traffic, one for the ABE traffic. It has also an additional so-called credit queue, which is also FIFO, and it has two class-specific counters, one for best effort and one for alternative best effort. And these credit counters act like a token bucket, where packets can only be dequeued if enough credit is in the bucket, and otherwise a next credit element is consumed. So when a DCD node receives a packet, it is first enqueued in their class-specific FIFO queue. Thereby, an additional credit element is created, which includes the information of the packet size and the packet class. It is added to the credit queue, and the ABE packets also are equipped with a deadline, which is the maximum allowed queuing time locally, for example, 5 milliseconds or 10 milliseconds. Packets are only dequeued if their class-specific counter has enough credit, and ABE packets that exceed their deadline are simply dropped. So there is no ABE packet that sees more queuing delay than the maximum allowed queuing delay. And when a packet is successfully dequeued, the credit from the credit counter is consumed. When there's not enough credit in the credit counter, the next credit element from the credit queue is dequeued, and the corresponding credit counter is increased by the size of the credit element. If the credit is enough, the packet is dequeued. Otherwise, the next credit element is dequeued. And the credit of previously dropped ABE packets remains in the system, which means that subsequent ABE packets can leverage this credit even before they are at the head of the queue, and therefore they can be sent faster, but they can only take a place of a previously dropped ABE packet. And therefore, the FIFO order of the credit queue somehow ensures that best effort packets see at least the same order and the same service as in a pure BE service, which is one of the main objectives of DCD. So with this mechanism, ABE packets receive low delay, but with higher packet loss, and BE packets do not see worse service than without DCD. You may have noticed that credit from ABE packets may remain in the system for an infinite amount of time, which is not desired, because then users may just send many ABE packets, they get dropped, but their credit remains in the system and accumulates. And then they can use it for later use, for later fast service. This shouldn't happen. And also, the credit and the low delay forwarding should only take place during congestion periods where it's really needed. Therefore, the credit should vanish when the congestion ends. Therefore, we introduced two devaluation schemes where the credit is devaluated. Once it is exponentially devaluated with a given rate lambda between two dequeue operations, and this can be expressed more easily with a half-life time, which simply means after one half-life time, half of the available credit is removed. And the second devaluation scheme is linearly with the link bandwidth when both queues are empty, because then the congestion period is over, and then we simulate normal dequeue behavior of the credit with a linear decrease with the link bandwidth. We implemented this mechanism in the Linux network stack as so-called egress QDisk. When we look at the Linux network stack, when we receive a packet is first enqueued in a so-called ingress queue disk. Then a routing or bridging decision is taken whether the packet is for the host itself or whether it should be forwarded. And when it should be forwarded, it is sent to the egress pod where the egress queuing happens, where the queuing happens, and there is DCD implemented. We need an exponential devaluation for the credit devaluation. However, the exponential function and floating point operations in general are not really possible in Linux kernel, or at least not efficiently. And therefore, we also presented an efficient approximation of the exponential function in the Linux kernel. And we also need the link bandwidth for the linear devaluation, which is unknown and maybe unstable. And therefore, we also have a precise bandwidth estimation algorithm that runs in the Linux kernel that measures the available bandwidth even at low link utilizations. Just very few details about the approximation of the exponential function. We do that with a piecewise linear function of 2 to the power of minus x. The details are not that much of importance. We have two different functions. We have one linear function f of x, which we use when the value of x is greater than some threshold, and we use another function g of x, which is the derivative for very small values of x, which are lower than a threshold. And we do this based on these two figures. On the left side, we see the approximations. Here in black, maybe it's not that clear to see, is the original function to the power of minus x. In green, we see the piecewise linear approximation, and in yellow, we see the derivative. And when we look at the error that we make when we use these approximations on the right side, we see that the derivative is better than the linear approximation for small values of x, and the linear function is better for larger values of x, and therefore we use the derivative for small values and the linear function for the other values. The bandwidth estimation algorithm is used for the linear devaluation of credit. It needs to estimate the current link bandwidth, not the DQ rate, but the real link bandwidth. And therefore, we use a moving average called UTEMA, which exponentially weights the sent bytes by the sent transmission time that it requires. We only do that when the queue is backlogged, so when there's at least one other packet waiting in the queue, so that we see the real bandwidth and not some random DQ rate. And this mechanism works even with low link utilizations. We see that in the left corner at the bottom, where we have a bottleneck link of 1 gigabit per second. The link bandwidth changes after 5 seconds to 250 megabits, and it changes back to 1 gigabit after 7 seconds. There's a special traffic pattern here. We have bursty traffic, where the offered load is only 50%. So on average, the link is only utilized by 50%, but still the algorithm estimates the real bottleneck bandwidth very closely. And even for the difficult case where we switch back from a low bandwidth to a high bandwidth, it matches the original bandwidth quite closely. Okay, enough of the theory, and now let's have some look on results and some plots. We evaluated DCD on a wide range of experiments. I will only show some basic experiments to show the intuition. First, we evaluated the efficiency of DCD because it looks rather complex with all these exponential functions and devaluations. We compared DCD with standard QDisks of the Linux kernel, FQCODL, FQPy, SFQ, and so on a 100 gig bottleneck link. We had 32 TCP flows. In the case of DCD, a 50-50 split between BE and ABE, and we evaluated the achievable goodput and the CPU load. And what we see is that almost all QDisks achieve the same TCP goodput of around 89 gigabit per second, which is the usual behavior on a 100 gigabit link. And we see the CPU load is also rather similar, but DCD has the second smallest CPU load, where only the really easy QDISC P5 has a lower CPU load, which simply means that DCD is implemented quite efficiently in a kernel and that it can even be used in 100 gigabit environments. The remaining of our results were conducted in the following testbed. We had a semi-virtualized testbeds with dedicated 10 gigabit network interface cards. We had multiple VMs up to 5 VMs sent traffic through a 1 gigabit DCD-based bottleneck. The bottleneck link was controlled by the token bucket at Polisa. We also had an additional RTT VM that applied a variable RTT on the path so that we were able to conduct experiments with different RTTs. Our default settings for all the experiments were the following: we had a 1 gigabit bottleneck link, an RTT of 100 milliseconds, a rather small buffer in the device of around 25 milliseconds, and the maximal queuing delay for ABE was set to 10 milliseconds, and the half-life time was 100 milliseconds. So after 100 milliseconds, only half of the available credit was still there. And to get an intuition on how the mechanism behaves, we first conducted an experiment with so-called non-adaptive traffic with bursts, which simply means we had UDP-based traffic patterns, so no TCP, no congestion control, but very bursty traffic with two kinds of offered loads. First, 95%, so on average, the link was utilized only to 95%, so no queuing, no packet loss. Only during burst periods we had queuing and packet loss, and then a second scenario with 120% load, where of course the link is overloaded most of the time, and only for very short periods we had less queuing. We randomly labeled 90% as best effort traffic and 10% as ABE, and the plot here shows the queuing delay for both ABE and BE for the two load scenarios. We had a varying number of half-life times on the x-axis, and also two different maximum allowed queuing delays of 5 and 10 milliseconds. And what we see here is the main property of DCD, namely that ABE receives less queuing delay than BE. We see on the left side of the figure around 3 milliseconds and 4 milliseconds, depending on the maximum allowed queuing delay, whereas BE traffic sees 8 or 9 milliseconds. And in the overload scenario, BE traffic sees almost all queuing delay of the device, which around 22, 23 milliseconds, but ABE still sees 3 and 6 milliseconds around queuing delay. We also see that with a higher half-life time, the queuing delay decreases because the devaluation is less hard, and therefore credit remains long in the system and can be used more efficiently. So the half-life time is a way to control the trade-off between loss and delay, basically. When we look at the packet loss in this experiment, we see quite the opposite behavior. We see that ABE receives more packet loss as BE by design. In the low utilization scenario, around 5, 4, and 3% packet loss, and BE sees around 0 point something packet loss, so almost no packet loss. In the overload scenario, we see at least 16-17% because we have an overload and there's not enough bandwidth for that traffic, and ABE sees around 4 or 3% more packet loss, and the packet loss decreases with a higher half-life time as before the queuing delay because the credit remains long in the system and can be used more efficiently. So this experiment validates the general principle of DCD, less queuing delay, but higher packet loss. A more interesting experiment is the following, which is, in our opinion, the main use case for DCD, namely that we have periodic UDP-based real-time traffic and general-purpose background TCP best effort traffic. This plot only shows the queuing delay for ABE. We have different sending rates of ABE from 300 kilobit per second to 100 megabit per second on a 1 gigabit bottleneck link, and we have a different number of background TCP flows from 8 to 64, and also different maximal queuing delays from 2 to 5 to 10 milliseconds. When we look first on the right side of the plot, because the left side is the special case, we see the order as expected. 2 milliseconds queuing delay result in less than 2 milliseconds queuing delay, 5 milliseconds with less than 5, and 10 with less than 10. And we see with an increasing number of background TCP flows, the queuing delay increases a bit because the congestion at the bottleneck is stronger. But we also see that there's no real difference in the queuing delay between 3 Mbit and 100 Mbit ABE traffic, so the behavior of the system is rather independent on the sending rate and on the traffic share of ABE traffic. When we look at the left side, we see a special case because when we have really low data rates, we have rather large inter-arrival times, so the time between two consecutive ABE packets. Many existing approaches that also do low delay forwarding with higher loss have in such a scenario packet loss in the order of 20, 30, 40%, because when an ABE packet is dropped, the credit is available, but until the next ABE packet is received, almost all of the credit is vanished, so that it cannot make use of it, and then the packet is dropped as well. To prevent such behavior, we have implemented in DCD that an ABE packet is only dropped if there's at least one other ABE packet in the queue that could use the credit, and therefore service differentiation is basically turned off in the case of very low ABE data rates, and therefore we see queuing delay as in a BE system. And when we look at the packet loss, we see again the inverse behavior. With 300 kilobit per second, we see almost no packet loss because service differentiation is basically turned off. And for higher data rates, we see a lower maximal queuing delay leads to higher packet loss because packets are dropped with a higher probability because it's more likely that they exceed the threshold. And with a higher number of acceptable queuing delay, the packet loss gets lower. But we also see that the packet loss is below 1.5%, which nicely fits the use cases from the previous table where we had acceptable packet loss rates with up to 5%. And we also see that the packet loss gets lower when we have higher data rates of ABE traffic because there are more ABE packets, the inter-arrival times are shorter, and therefore credit can be used before it is devaluated. Yeah, this brings me to the conclusion of my talk. We presented DCD, which is a high-performance queue disk that supports ABE and BE scheduling. We implemented it in the Linux network stack. It is capable of achieving 100 gigabit per second. We also presented an efficient approximation of the exponential function, which is used in our use case for credit devaluation and bandwidth estimation, but it could be used for any other mechanism that needs the exponential function in the kernel. We also presented a bandwidth estimation procedure that works even at moderate link utilizations, which is rather difficult. And our experiments show that DCD offers low delay solvers for ABE without degrading the best effort traffic, and that ABE is able to turn packet loss into a delay advantage. In our paper, we also did experiments with TCP traffic that also reveal that you have to be careful what your congestion control does when you have different AQMs in your network. But this is for another talk. So if you're interested in that, have a look at the paper. Thank you very much for your attention, and I'm happy to answer any questions.
Thank you, Stefan. And we already have Richard in the queue.
Hi, Richard here. Thank you very much. It's a good presentation. I like it, like the topics you presented. But there was something, a few points I'd like to have your clarification. When we talk about best effort, usually that's a function implemented on routers. But from your presentation, it looks to me, so all this kind of thing would be implemented on the host. So there will be no changes needed for routers. Is that true? Is that a fair statement?
No, so DCD has to be implemented on the bottleneck. Because only
on
there,
the bottleneck.
On the bottleneck, so on the router where the bottleneck occurs typically. Or where
So,
we have
okay. Good enough. So suppose you said implement on bottleneck. How do you know it's going to be, which router would be a bottleneck?
Well, of course, we do not know that, but in principle, the mechanism only affects the traffic at the bottleneck. So even when it would be deployed at multiple nodes, those nodes that are not a bottleneck don't have an effect, and only the bottleneck link has, or the bottleneck node has the effect.
Yeah, but internet traffic usually it's boosted, right? So we cannot make an assumption like a particular router would be a bottleneck, right? So in order to make this mechanism work, so you have to implement it everywhere, just in case that router would become a bottleneck someday, somehow.
Yeah, or you know
Right.
based on your statistics that it's more likely that some node is a bottleneck than another. Yeah.
Yeah. Okay. So I'm clarified. So signal one is that. So sometimes when we implement reliability, right? So it doesn't have to be TCP based. We can still use UDP, and we implement those congestion control functions and reliability functions through some libraries on the host there, right? So suppose we do that on top of your ABE here. So overall, will that performance improved or not? For some, there's another like protocol, right? It's still a transport protocol, like, which is actually based on UDP, that kind of thing. So I assume we can use ABE there and to support this. So my intuition is that it might be, but I'm not sure in your research or experiment, you have any results on that or not.
Yeah, sure. You can combine different kinds of control systems on the host in combination with DCD, but you have to be careful because, of course, DCD has the implication that you have higher packet loss. So when you're talking about reliability control mechanisms, then it might hurt your applications when you tell the system via your DCP code point that you are ABE traffic, but you rely on end-to-end connectivity and cannot cope with, let's say, 1-2% packet loss, then it might be better to still use the best effort service. So this is really intended for traffic that can cope with packet loss. Then, of course, you can incorporate any other mechanism. You can combine DCD, for example, with Cordell or any other AQM on the router itself, but you will have the implication of higher packet loss. So whether this is acceptable or not depends on your use case.
Okay, I get it. So now it comes to interesting part. Suppose on the host there, I have two queues. One is BE, one is ABE. On top of them, I implemented some reliability functions, and by using library, like in order to implement another protocol. So in this case, for these two queues, are they going to share same like a window control, like a parameter, or they have different like parameters for the same application? Because same can be some traffic, like maybe you would like to put it in the BE queue, another type of traffic you would like to put it in the ABE queue.
There's nothing limiting one specific rate of one of the queues, but you will, as by design of the mechanism, you will always serve the ABE queue if you have enough credit. But that implies that the BE queue has no credit, because otherwise the BE queue would be served. But besides that, there's no control mechanism that decides which queue is served, and therefore it's not rate limited or anything else for your upper reliability function.
Thank you for your question, for your answers. So the last one is no question, just to give you some information. And for some volumetric multimedia applications, this work is important, but there are other approaches to address it. For example, in some community, people are working on something called qualitative communications. Typically, that's for volumetric video or AR, VR, even holograms application. So they are faced with same problems you are trying to solve here. But that's called qualitative communication. Some people call that the semantic communication. It depends on who you are talking with. Thank you.
Okay, thanks.
Okay, thank you, Richard. Do we have anyone else wanting to ask a question or make a comment? In fact, I have a question. I'm curious. So you mentioned some applications can tolerate packet loss up to maybe 5%, but then some of your slides, we saw packet losses that were much higher. So I'm wondering if it's possible to have an upper bound on packet loss, if there's any way you would be able to incorporate that.
in the case that ABE traffic is not too high, so of course, if we have an overload of ABE traffic, the packet loss is basically unbounded. But for UDP-based traffic, we did many experiments and we did not see packet loss higher than the 5%. We did not make a model to assess whether there's a real upper bound, but this would be of interest, of course. We may have a look at that. Yeah.
Okay, thanks. And then we have Tianji in the queue.
Can Chairman well. It's not specific for this paper, but I have some general comments. Something we are facing right now. It's related to internet congestion control, but it's more with some coordinated actions. In the 5G system, there are some components. Well, basically, like you have radio, like a base station, and you have UPF functions, and those will participate in the end-to-end flow. So basically, you can use like the one you just described, or any other congestion control mechanism. Because there are some mechanism to associate between two entities. Here we talk about the GNOB and the UPF, but in general term, if there is some way to coordinate between two entities, so when one entity determine or find some problem like congestion happened, well, at that time it may send a QoS notification toward the other, such that the other can do the marking without doing like sending the traffic toward the receiver and then do a turn back. So basically the work can be done in the middle of the node in the network. It's going to save you a lot of on the round trip time, so that the marked thing can be sent back toward the sender from the middle of the entity. So this is something, although at this time the 5G were using it, but at that time it's not going to turn around, and the UPF function, actually UPF function will still send on the original direction, so that the receiver, you can consider like the UE to receive it with the tag marked, and then it's going to send back to the sender for sender to do congestion control. So just like something I'm trying to think aloud, say, okay, well here, since this is a research group, so I give some, just some things for people to think about it. Whether based on the, like you can consider upstream QoS notification, such that you can save some round trip time. Thank you.
Okay, thank you. Anyone else? Going once, going twice. All right, thank you, Stefan, for your presentation, and thanks everybody for the discussion. I'm sorry, I thought I heard somebody say something. All right, so that is the end of our agenda. Yeah, thank you everybody for participating today, and thanks again to our note takers.